Zaplá přítá. Poták prostě.
Tak ona vlastně ta pěna ani moc vody nepotřebuje, že jo? Tam dá saponá rozduch.
A to by se bavilo.
Takové vysvětlo, ne? Už dvě? No, tomu nesvítí a Jirkovi prý taky nesvítí. To je nám to nějak fakt celý. To rozbitý prostě.
Trochu?
To si potřebuji muset vyměnit, no. To jsou dvě rezervní, no. Tady. Jo, dobrý. Takže budeme se přivést plošinu.
A to říkáš z naší strany?
No.
Já
No
se
jako
ještě podívám na tu dálnou
teda
prezentaci.
to nevadí, protože to se podívám, ale tam to svítí na to.
Photonic Trends, což dá číslo.
Musíš se ten otoček všimnout?
Kdo?
Jo, teď jsem to říkal. No, já už jsem to řekl, říkám, ale svítí ti
A jo.
Za finální zkoušku toho prezentéru.
Ale prý jsme zítra nebo do 11 oběti.
Co?
Zítra.
Co ano? Vytáhněme tady. Mikrofony fungují. Tady třeba půl. Já jsem ještě nahlas. Takže na to ani ne. Že pan musí propat zubou. Co tam furt bude? Jsi stáhnul ten? Jsi zašel na letu? Prosím tě, jsem na letu.
Tak,
dobře.
Vážené dámy, vážení pánové,
Máš nějaký job?
zajímalo by mě odpustu za to posvíkočko.
Jsem tam i já? Nejsiš tam. To by tam dali jako ze světláme. To by viděli, že máš zájemčí. Kdyby říkal, hele, ten Pavel už nebyl dlouho nemocný, já mi tam dám preventivně 14 dní. Ty jsi tady, tady ten řek. Hej, to je řek. Ty no, to je tohle.
je Petr?
Sakra, to nemám polici telefon.
Co? Jsem instalace. Ale... Tam něco běží už předtím. Co tam ještě? Předtím? Co? To bylo mít. Ale víš, že to je to nic. No, Amerikáni. Dneska do dítě. Co? Dneska do dítě. A jdou. Teďka, co bude? Za rok. Já nevím, to jsem čekal, že jsem něco slyšel, jestli jsem něco, tak já taky jsem něco slyšel. Tak já nevím, že něco slyšel. Já jsem se jako převratnou novinku, jakože se chystá říct. Ale slyšel jsem o iPhoneu 5, ale já 4S tedy... Takže dokonalej fakt, jo. Bude mít ten APET 5, to si ale jo, konečně spoustě našich videa. Třeba se potřebuju, docela jako...
To neuflashový videa.
Oni to nepopodujou. že naše Spatial, proč jako neudělali přehrávač, tady to podporuje někdo jako... Protože by se to musel nainstalovat v App Store. No, tak jsou krklíky, že jo. Asi nestavuju, já už to mám krklí, tak stavuju. Tapety a...
Třeba má nějaký emulátor, jak má nosí to vynapit, tak musí to doznat, že bys tam narval nějaký jiný byl.
To prostě nevychovuje, takže protože to je strašně byla hardwareově náročný. Hardwareově náročný. Ano, teď oni spíš, ale jako prostě asi s tím nejsou kámoše, ne? Ne, takhle je strašně náročný do Flash, no. Je normálních to...
Třeba můj notebook s tím má obrovský problém.
Tak tvůj notebook, vole. Jako je to fakt náročný, zbytečně úplně právě. Říkal, ale třeba Vimeo a YouTube, vole, prostě jako programy to dělají jinak, ale dobře. A funguje bezvadně. A to Flash prostě je zbytečně náročný. Strašně vyžere baterku a přehřívá to prostě. Protože to pak není takový... Jednička, vytáhni. Raz, dva.
Nemám včera
Jak to zvládne, ale prostě on nechtějí.
Tak železo to na test.
Až se nasedu, tak si... Ne, ale není to takový prostě, že jako klik a je to tam. S Androidem a to prostě neudělá.
Není to tak svižný.
Prostě není doplácky svižný, to není jejich styl. Ale to strašně žere baterku a přijde ten telefon.
Tato operace, co čteš, to je zajímavý.
Nějakou operaci. A vedle operou třeba 3Dčku. Jako prostě nějakou
Prostatu tam děláš.
Fakt to.
Víš, ten tunel, ty vole, jak tam mě hrabou ty robotický pracky.
Je tam močová trubice.
Víš, že máš močovou trubici, jo?
To vím, to je pod tím tukem, no.
To máš pod tím sádlem.
To máš pod tím sádlem.
To máš pod tím sádlem, no.
Aha. No tamhle to je asi červené.
Ty tam měli normálně na streamu toho chirurga. Co to dělá?
Jak bych řekl červené tamhle.
Je to zapnutý?
Já bych se vás koukal jenom vytáhne vždycky.
Jo. That's okay. It's a little. Yeah. I have no words. Is it okay to put in the packet? Or? So, like this?
Okay. Good afternoon, ladies and gentlemen. I would like to invite you into the optical networking session. Welcome on the conference. And my name is Jiří Navrátil. I am a chair of this session. I come from the CESNET. And we have 3 talks. I would say the first one show us some future. The second one show us some practical experiences, and the third one show us some new type of application which could be run on the optical networking. And I would like to ask the first speaker, Kurosh Bozor Geibrahimi, he is from the Uninet, Norway. And as you can see, his title, Photonic Trends in the Future Networks. So, 30 minutes is yours.
Thank you. Good. Hi, everyone. As you see, the topic of my presentation is photonic trends in the future networks. The topic is very broad and almost impossible to cover during 30 minutes. I am also not capable to to cover all aspects of photonic technology and optical fiber communication. So if I was capable to it, also the 30 minutes, not so much time. So my colleague, the colleague in CESNET, Joseph and Pavel, in the framework of John 3 project, JRA1, Task 2, photonic groups, we picked up some topics which we think that it should be interesting for you. So it's far away, everything, but it's just some topics. Just want to have you in mind. I will go through these bullets, these topics. First, going through the motivation behind recent research activities, and also take a look to the optical transmission evolution, which happened last 2 years, and the direction of it, and also see a little bit ROADM evolution, optical switching evolution, and also the concept of open transmission system. My first slide is shows about the capacity growth, because always the capacity is issues. The researchers have to know the capacity growth and how it will be about 10 years from now in order to make the right decision. So according to US data network traffic from the statistics gathered from US data network traffic, we see that we have about 58% of traffic growth per year, and if we translate this to the optical transmission networking engineering language, so it is about 2 dB per year. And if you see also it's line with the growth in processing in the supercomputers, so it's the parallel. And also, which is important to mention, that the new services which coming, cloud computing services, and also video on demand services will also maybe push the traffic growth even higher. So it maybe go from 2 dB to 2.5 and even more. So it's something to have in mind. The lower picture actually shows the evolution of capacity, and both in the research area and in the product area. If it goes, for instance, see the WDM research activity capacity and the product, we see that is about 6-7 years is about time differences. So if you see something happening today in the research area, so maybe you can expect to have it about 7 years from that time. So it is an interesting figure. But also the other, which is the signal channel electronically multiplex interface rate, have also constantly scaled at 0.5 dB per year. As you see, the scale rate, it was about 4 times, 2.5, 10, and more. But also you see the serial interface rate in the research area, and also this is the interface rate. As also serial interface in the which is in the product. And what other also maybe important thing which we can learn from this figure is that the router interface evolution also getting closer and closer to the serial interface products, which is on traditionally SDH and WDM and ODU interfaces. Is according to the development which is going on in IEEE and ITU-T, which we have 40G and 100G and so on. In order to handle the tremendous data traffic in the future, we need actually also higher bit rate single channel electronic multiplex interface rate, and which is obviously that the increasingly widening of technological gap between desired interface rate and cutting-edge serial transmission research will force future interface to adopt an increasing level of optical polarization instead of serial. So it is some important factor. One other slide, which has introductional, I will share with you, is the fact of Shannon limit and fiber capacity. If you ask maybe most technical people about the fiber, when they deploy the fiber and ask them, okay, what's going on with the fiber, they're saying that, okay, fiber is there and it can carry unlimited amount of bandwidth. But it's not quite true, actually. Fiber also has some limitation. So you have the famous Shannon capacity formula, which say what's the achieved capacity. It's proportional with the bandwidth you have and the signal noise ratio which you can achieve in your system. We know that the bandwidth in the optical fiber is limited to somehow. So the only way to increase the capacity is to increase the signal noise ratio. And it will gives us higher capacity. It is true actually in the radio RF communication field, but not quite true in the fiber optical communication. So which is very important is that the fiber optical fiber communication, we have two areas. The one area is dominated by noise, mainly from ISA, and the other one is from the nonlinearity. The fact is that if you, in order to get more capacity, so you have to depress the noise and increase signal launch power. When you increase the signal launch power in a certain point, it actually can get megawatt of power per square centimeter. So it's as we're talking about huge power actually. In certain power, the nonlinearity will occur and the capacity curve will go down. So it's not so easy to say that, okay, with launching more signal power, so we're getting more capacity, but it also has some limitation. And it is happening due to Kerr effect, which is a known nonlinearity effect, and it's due to that the core index of refraction actually affected by the presence of the signal, and it will also make a kind of phase rotation in the signal, but this phase rotation in conjunction with other distortion which you have in fiber will cause that the amount of capacity goes down. So it is very important to this one. As I borrowed these slides from Alcatel-Lucent, which also I borrowed from some other paper, which is from 2010. It's showing that okay, they did some research and they find out that okay, the capacity limit actually on fiber is about if you divide capacity to the bandwidth, so you get the spectral efficiency of I-fiber. So they're saying that okay, you are getting about you can get about 7 bits per second per hertz of spectral efficiency, but maybe no more. But so it is per polarization, not per. It's very important to have in the mind. If you have dual polarization, so then you have double this one. But the other important one is that a recent experimental result shows that we are in this area here. So we have about 2 to 3 times of growth rate. So we can grow 2 to 3 times and no more. Then we have to do something special. So I guess that these two, the capacity growth demand and the fact that we have some limitation in the fiber is also set some premises to how a researcher works actually. Again in 2010 in European Conference on Optical Communication, the keynote speaker for Nakazawa, Professor Nakazawa from Tokyo University, he talked about three breakthrough technology, which he called 3M technologies. The first one, which he meant that it will be very important in the years come. And the first one was the ultra multi-level coherent transmission, a kind of multi-level modulation, which we actually seen it. We can see some development of this now in the here, but also new optical fiber technologies. He especially mentioned the multi-core fibers. But I know that a lot of work is done and is in the field of optical fiber. You know, you can find optical fiber in each categories in the access core with different purposes. So multi-core fiber, transmission over multi-core fibers, which I'm going back to it, and also starting to use multi-mode fiber and multi-division multiplexing, also a kind of a new space, a new dimension of physical dimension of transmission. Here's some a picture which shows what's in the transmission field, what possibility you have in the modulation and multiplexing. You have in the time, in the intensity, quadrature multiplexing, code, frequency, polarization, and already when we are going from 10G actually to went from 10G to 140G, so actually we start to work in this and take benefit of more advanced modulation system, QPSK, QAM, 16, and so on. But this advanced modulation is not free. It also have some cost. It comes as part of, because when you increase the constellation points, so you also increase the demand for signal to noise ratio. So so it's something which you have to in your mind. But which one other physical space, a physical dimension which wasn't used yet is the space which they are going to use it more frequently. Is if you're going to some research activities, seeing that there's a lot of work is nowadays is done in the field of spatial division multiplexing, actually, both with multi-core and multi-mode, which also I will show a couple of them. Here is a work which is presented in UFC 2010. It is, I guess, it is the highest bit rate of transmission which is achieved so far. It uses a combination of technique. Actually, it's used the polarization division multiplexing. It used the wavelength division multiplexing, 16 QM. Also use both the C band and L band. As you see, it consists of about 432 channels and 171 gigabit per channel, which you get about 69.1 terabit per second of capacity. Is achieved over 240 kilometers. So it said that from on-off keying from a simple transmission system, so we are moving to a more complex and use a variation of different technique. But all of this technique actually, we can use a mix and match of everything. But the important one is that we have to keep and take off orthogonality, actually, when we do it. Is it a super channel? Also, it's another, especially when we are moving from 100G above toward 1 terabit per second. We are saying that it is need to use maybe broader bandwidth, and the super channel actually is a single laser source, which is frequency locked with frequency locked carriers. You have at least two sources of it, but the detection part is the same. It's some recent activity research which is done in this field. You see here is, for instance, using 7 carriers, 2 carriers, and different 36 carriers, 50 carriers, and they also we are talking about a single channel here, but a broader single channel which consists of subcarriers. One recent activity, research activity, which is done, experiment, is achieving about 11.2 terabit per second high capacity per channel by using 112 optical subcarrier, and the subcarrier have about 25 gigahertz spacing. So it's one channel, but the channel is not 100 gigahertz or 25 gigahertz or 50 gigahertz. It's broader, and actually also this brings the issue about multi-grid functionality and availability in the network, which the future network should also handle, not be fixed to some specific grids, but have to be more flexible and gives the flexibility to use a mix and match of grids. The other one is some research and some work which is done in the field of optical domain, and also switch about 10.2 terabit of transmission, 40 gigabit base channel rate, and optical time division multiplexing by factor of 128 using passive fiber delay multiplexer, and they achieved about 10.2 terabit per second. Now going back, coming to the field of spatial multiplexing, spatial division multiplexing. In this field, there are two main technologies using. The first one is the multi-core fiber, and the main issue with multi-core fiber is the crosstalk between the different cores, especially when you bend it. But in order to handle it, they can design the fiber in a special way. This is one example. If you see the core, the first core, the main core, is about 9.2 micrometer, and also you have the outer core. The odd and the even part is one of these two, is a little bit higher core, about 10.7 micrometers diameter, and the other one is about 7.3 or something like that. So, and also, as you see, also attenuation is about 0.2, around 0.2. Is this fiber. So what are they going to do as to use all the core for the transmission, and use the so-called SDM, spatial division multiplexing. But also you can do it with the multi-mode fiber. As you know, you have some challenges about mode coupling, and also intersymbol symbolic interface at the receiver side. The ordinary multi-mode fiber, as we know it today, is the G651. You maybe have more than 50 and even more kind of a different mode in the fiber. But the the new multimode fiber, or fiber which they have intention to use it for the transmission, especially long distance transmission, but this in transmission in conjunction with the special division multiplexing, they have less mode than the ordinary multimode fiber. So you will see the fiber which they call it for few mode fiber. You will find the fiber which they call it for 2-mode fiber or 3-mode fiber. So they are creating a fiber which is a kind of multi-mode, but with fewer mode in it, in order to be able to handle it. Actually, different modes and interconnection between modes, and it will make it easier. I have 2 examples of the recent special multiplexing experiments based on multi-core fiber. Okay, multi-core fiber. The first one, as you see, is they achieved about 109 terabit per second of transmission over 16.8 kilometers. Here they are using 7-core fiber, which I showed you in the last slide. And each STM, each core contain 97 with WDM channels, and each channel actually, which 100 gigahertz spacing, carry 86 gigabit bit per second of traffic, but also they are using also polarization division multiplexing. So here you are using special division multiplexing, wavelength division multiplexing. You are using polarization division multiplexing, and you are using 16-core arm, also current receivers, also so on. So as also this one, I have a limited time. So this is also another example of experiment which also use the multi-mode fiber, the multi-core fiber is again 7 times 80 times 107 gigabit per second. This also shows 2 examples which are used in conjunction with the multi-mode fiber. The first one is a special design which is 2-mode fiber actually. They also use dual mode and dual polarization current over a dual mode fiber. The second one is a few mode fiber, but they are using only 2 mode of it, and 2 times 100 gigabit per second of traffic they are carrying here. How much time do I have?
Yeah, so you have 1-2 minutes
What?
plus
Yeah.
for some questions.
So that's actually conclude my my presentation about the transmission evolution. My message is that you can carry traffic in many ways. That anything might be limited to the means you have actually. So and imagination. So you find a solution for it. Talking briefly about ROADM evolution. The ATWA workshop this afternoon. They have 30 minutes of presentation. I see about ROADM evolution. So it's 4 stages of revolution. The first one we used fixed OADM, optical add-drop multiplexing, typically with 3-mode fiber, 3 ports fiber, and also it became a 2 degrees 2 degrees ROADM, reconfigurable optical add-drop multiplexer, and further we went through the colorless, directionless, and contentionless based on WSS, which you see here. But the last one, which also we are not there yet, but which also will be the next one. Next big thing in ROADM is the handling the grid in order to handle a variety of bandwidth on the optical networking. I have some slides optical packet switching. The main motivation behind doing that is the overcoming electrical speed bottleneck and transparency to payload modulation. And we are kind of doing some power saving, as you see also in this slide, with low bit rate or low switching speed. Actually, the power consumption is the same, but when the amount of traffic grows and we are going to handle more and more traffic and bigger switching, packet switching. So the huge benefit of optical packet switching rather than electrical one. Also, it used a better network utilization, higher network throughput. It's rather a lot of time to cover all of this, but you have a variety of way to make it happen. You have some obstacles. Actually, the main obstacles with the optical packet switching is the buffer and the buffering. It's not easy to make. Here also you can see some way to do it. Optical switching methods that you have the broadcast and select one, which you send actually all incoming packet to the all ports, and you have some kind of very fast selective ports which can let the packet you want go through or stop the other one. But also you have a variety of way to make optical buffering. The last one is maybe the main important one, is a slow light, which you can achieve about 10 times buffering. Actually, you're slowing the light 10 times. But all of this is a very early stage. I'm unfortunately can't have none time to cover, but just going to the summary. All the presentation is available on the web, so we can just read it, the last 5 slides. We see a shift in complexity from optical domain to electrical domain, doing dispersion compensating at the receiver side and the DSP level. We see the both. You can do it both the PMD and CD in the DSP level, using unused physical dimension such as space by employing a special division multiplexing and using broader single band to carry capacity, need flexi grid band. We also see the cost-efficient ROADM based on colorless, directionless, contentionless, and gridless. Optical packet switching is still far away as a commercial product actually. And we also see we just didn't cover that at all. There's open software improved our possibilities significantly, but we are seeing that we're looking for that open photonic transmission system also doing the same. It's the same concept. So that's conclude my talk actually.
Okay, thank you, Korosh.
Thank you.
And we have a time just for one small question. So, somebody? If not, okay, thank you once again.
Thanks.
And the second speaker is Lars Lange Björn from the NorNet. As I said in the beginning, he will talk about the experiences with the DWDM 40 gig on the cross-border between the Netherlands and Denmark. So, next 30 minutes is yours.
Thank you very much. Yes, I'm here to talk about the design and OAMP aspects of a DWDM system equipped with the 40 gig PMQ/PSK alien wavelength and adjacent 10 gig channels. So ever since I joined the NREN community, we have talked about alien wavelengths. It's still a I think, a hot topic, especially as the involvement of modulation schemes and the better control in the optical domain of the spectrum. It makes it now possible, I think, to, or at least it's more possible to arrive at that stage where we can make predictable performance for alien wavelengths. My name is Lars Lange Bjørn. I'm a manager of the optical network department in NorNet, and I have made this work with the Roland Neutsch SurfNet, Martin Nordahl Petersen, and Anna Vasileva Manolova from DTU Photonics. Let's see here. Yeah. First, I will talk a little about the history of this setup. I think many of you have seen or heard about this setup a couple of times. Even today, there was a presentation, the first, the plenary session with Cees de Laat. He was actually using this setup, so I will just go through the history, so I'm not repeating ourselves again. We have actually changed something. Then I will talk about the design, and I will talk about some offline simulation we have done, compare those to the experimental results, talk about OAMP, which has been a bottleneck, at least from my perspective, a bottleneck for implementation of alien wavelengths in the different systems. We're talking about cost consideration, and then at last the conclusion. So, April 2009, got a call from Roland suggesting that we did an alien wavelength in the cross-border fiber between SurfNet and NorNet, where we are joining in Hamburg. And at that point, SurfNet suggested to use PMQPSK coherent detection on a 40 gig, because that was the only coherent scheme that was available for terrestrial communication at that point. So we have a compensated network, dispersion compensated network, and SurfNet has an uncompensated network. So that was the only possibility at that point. So we moved quite fast. In September 2009, we were ready to go with the installation. November 2009, we had the Hero experiment up and running. We presented it at Supercomputing, Portland, Oregon. And the ability of both networks were tested, and we identified several shortcomings, both hardware-wise, software-wise, and so on. But we were able to operate it with unoptimized condition with below 3 times 10 to the minus 16th. I think we run it for roughly 20 days without any errors. So this is after FEC correction. It's not pre-FEC. June 2009, Roland was in Vilnius presenting also the setup. At that point, we had done additional simulation in the Shannon optical modeler, where we tried to simulate the Alcatel illusion network as well. We were able to run it in a more optimized condition and running below 10 to the minus 17. So here we are today, May 2011, and you wonder what's new, right? So let's see here. Well, this is the initial setup. Let's see, I can point here. This is the start in Amsterdam, going through the amplification chain to Hamburg, and we interconnect directly here from a passive DMUX to an active coupler, and go all the way to Copenhagen. So the new things we have added now is we have added the 10 gig neighbors here and here on both sides of the channel. We have a ability to make a guard band variation very easily with the Alcatel illusion. We can change the wavelength, we can change the filters very fast, so we can make these variations. We have done it now for 50 to 150 gigahertz on each side. We have full control now of the spectrum. We had a little issue with some hardware, software, actually software down here. Now we can control the spectrum very well, so we don't jeopardize the existing channels. And we have added to everything on top of this. We have made some offline simulation in a, let's call it a generic simulation tool, where we try to model both Alcatel and Shannon equipment at the same time. So starting by looking at the VPI simulations, well, our goal was to make a verification of the experimental results. We wanted also to facilitate the design and control of the current setup, because The operational window we found was very, very small. Either we had the channel running or we didn't have it running. It was very, very small variations in both 10 gig and 40 gig. So we would like to have a VPI simulation saying, where are we actually? Are we on the good side or are we bad side of the optimal configuration? And then, of course, we would like to investigate an option for future multi-domain, multi-vendor simulation tool. I think all vendors, they have simulation tools, and they have the knowledge. They could make these tools for us, but I don't think they will do it. They will stick to their own. So I think if the NREN community wants to see something, we have probably to make it ourselves. So the challenge here with VPI is that we would like to obtain all needed information about the components. It's quite difficult to get out of Shannon and Alcatel the exact specification for all the components. But the next thing is it's quite complicated to do this in VPI, although there are predefined models for everything like amplifiers, fibers, dispersion compensation. You would actually also like to know the exact configuration, but if you do that, it just explodes in VPI with the work to do. So this we want all the information, but we only want the critical thing and put it in. So we have tried that. I'm just showing here the initial configuration in VPI, and it consists of this is the Amsterdam section, Amsterdam Hamburg section here, Hamburg Copenhagen, and then we have all this is Copenhagen. So I will just go through it here. So Amsterdam, this is the 40 gig PMQ PSK injection. This is modeled by two different polarization of a 20 gig signal. We have the additional 10 gig running in the SurfNet network. It goes up here to a multiplexer and go through and a preamp belonging to the SurfNet. Next is the simulation of the TrueWave RS fiber going from Amsterdam to Hamburg. Consists of 9 amplifiers and no CD compensation. We have the Hamburg side. We have a DMUX. This is you can say the Shannon DMUX. Dropping off the 40 gig, it's running here. And then we are adding the neighbor channels, 10 gig NRZ. And then we have also a preamp amplifier from Alcatel. The next here is TrueWave RS as well, going from Hamburg to Copenhagen. We have 4 amplifiers. It's with dual amplifiers with mid-state axis, allowing for the dispersion compensation, chromatic dispersion. This is modeled in VPI with a normal amplifier, and then of course with the spool of dispersion compensation fiber. And we have 5 instances of those. That gives 10 amplifiers. And then finally we have the Copenhagen side. We have an OSNR adjustment and control. We have a filter here. This is representing the wavelength selective switch used by Alcatel. And we have then this receiver, PMQ PSK receiver with the DSP. And in VPI you can even model a certain variation of the DSP. So all these components you have seen here, they have a multitude of constants you can change, and it's very difficult to find out exactly what it is and what is the influence of this in the long run. But this is of course the goal of the simulation, finding out how much do we need, finding the limit for it. So we have some rough assumptions if somebody wants to try to make a similar approach. We have the noise figure assumption of 5, OSNR at 20, PMD, nonlinear index for the dispersion compensation fiber. The method used is a Monte Carlo approach, where we have 50,000 bits per data point. I'll show you the next slides how many data points we have, but it's a quite long simulations that we have done here. It's not trivial to do this. With nonlinearities enabled, we have 3 to 4 hours per data point. So even though we have computers, it's going awfully slow, we think. And without nonlinearities, it's 15 minutes per point. So these are the first result that we saw. This is 10 gig variation on the x-axis. On the y-axis, we have the negative log to the prefect bit error rate on the 40 gig. What we see here, if we take, for example, the power for 1 dBm in the 40 gig signal, is that when you increase the 10 gig power, the degradation of the BER is evident. And similar for the 3 and for the 5 dBm of the 40 gig. So this is quite in correspondence with what we know. We have a cross-phase modulation between the 40 gig and the 10 gig. But looking at the graph, you will also see that you actually get a better BER by increasing the 40 gig signal. So we were a little unsure, have we got the parameters right here, because we should see some self-phase modulation. So we turned off the 10 gig and tried to do a bigger sweep with the 40 gig. And this is the signal we came out with. And as you saw before, we were going to 60 dBm on the 40 gig power. But when we go to 7 and 8, we have a very big degradation of the beta rate. So this really shows that we, in the previous slide, just go back, we were actually just approaching the next point, that we will see a swap of these channels here. So it's evident here that we have a very strong degradation of the beta rate when we go above this. I should say also that these power measurements down here, they are not absolute. They cannot be compared to the real experiment. These two should take just compare them with the 10 gig. So adding those two informations together, we have again on the y-axis the minus log to the prefec. This now on the x-axis we have the 40 gig power, and we have a variation of the 10 gig power. And here we see that you have this waveform here. You have an optimum on all 3 lines, which means that there's a sweet spot somewhere. And when you increase the 40 gig power, you cannot overcome the limitation of the BER, or you cannot overcome the increased cross-phase modulation that is seen from, let's say, the 6 dBm. You cannot overcome this and go to the 3 dBm curve by increasing the power of the 40 gig. So these are the experimental results for 50 gigahertz spacing. In the background here we have the 10 gig power is off. So we see here again, when we increase the power, you will see that the degradation of the beta rate goes down, which confirms the theory of self-phase modulation. Adding also the 10 gig powers, you can see here that the power of the 10 gig signal have a strong influence also on the performance, and it goes down here as we increase the power. These areas here, we were not able to monitor those. There was just the ability of the network element could not detect lower than 10 to what was it? Minus 0.5 times 10 to the minus third. Similar for different spacing, we did the same experiment. For 100 gig spacing, there's a small improvement between these and the previous graph. And we also have, for the 150 gigahertz spacing, an improvement again. So these graphs here say that the spacing between the 10 gig channels and the 40 gig channels has a very big importance, and the power of the 10 gig and the 40 gig has a very big importance as well. So it's very difficult to find the sweet spot. But anyway, let's look at what's really is interesting here. It's because we talked about previously also about guard bands and so on. Well, this is how it looks when we have 10 gig power at minus 20.7 dBm, and we are varying the 40 gig again. You'll see here that we have the 50 gigahertz, and the red line is 100 gigahertz, and the green line is 150. Clearly says that I think a guard band is needed for these kind of applications if we're running PMQ PSK. To put it in perspective, when you are using the Alcatel design tool, it says that the 10 gig power, in order to maintain the guaranteed performance in the traffic matrix, should be minus 17.2. So not even if we were with 150 gigahertz spacing and we increase the 10 gig power, I'm not even sure that we will have 10 to the minus third. So this is an important lesson, or at least something to think about when we are talking about alien wavelengths. Do we sacrifice? Do we have a very large guard band? This is special for PMQ PSK, but that was the only one available at the time when we started the experiment. Now with the new modulation formats, 100 gigabit coming, it could be that this actually would look better, because 40 gig and 10 gig is notorious for not working very well together. So, why are we having all this discussion about OAMP? Well, let's look at the standardization. We have two standardizations that talks about alien wavelength. G698.1 and 2. But the problem with those is that the scope actually is, and this is taken directly from ITU homepage, it's intended for metro applications. It's only also for single interface operation between two different systems. And it's only applicable for 2.5 gigabit and 10 gigabit at 150 gigahertz spacing. So it's not really for what the NRENs are looking for. I don't think we can count on the ITU making the work for us. So what we have of an issue in the NREN community is that we have no transverse compatibility between new long-haul modulation schemes. No, not that much work is being done to go further than 10 gig. And with the new 100 gig, although people thought that OIF would make it a standard, it's actually going only an agreement. So you will not see 100 gig transponders work together from different vendors. I don't think so. The thing is that everything, the receivers and the DSPs are not single source. That would be from multiple sources, and different vendor will try to optimize there for their applications. So you will not have those two talking together. And there's no standardization target on optical transmission section and optical multiplexing section. So this is only single wavelength. So I don't think that was what we thought in the NREN community a couple of years ago. Probably we thought that we could melt everything together. But as a consequence of this, I think that the NREN targets must be, when you are looking at new equipment and thinking about what to look for, the advantages between the different vendors, is that you must have full optical transparency with bit rates, modulation formats, with spacing. You must have full optical control. You must have control of the power. You must have control of the spectrum. And you must have some kind of admission control, so you don't let in alien wavelength into the system that will destroy the system. Chorus talked about flexi-grids and so on. This is especially for the new modulation format, super channels, that will probably utilize several different carriers with a very close spacing. And of course the power, you still have to have control of that. So taking into account, we are looking at the setup that we have here. We have the bitrate, modulation format, spacing, power, spectrum, and admission, and then mapping that to our setup here. This is a simplified drawing of the Alcatel receiver, add and drop complex. And I have listed down here the bitrate, modulation format, spacing, power, spectrum, and admission control. But I can see that this presentation is not compliant with mine, but the red should go up here. So, okay, at the A we have the add to the system. This is bitrate transparent. It's modulation format transparent. Spacing what's it called? It accepts any spacing because it's a passive coupler here. Then at B, this is the add to the spectrum. It's also transparent to bitrate modulation formats, not to the spacing, because this is a 50 gigahertz filter. You cannot control the power, you cannot control the entire spectrum, but you can shut down the channel. Most importantly, we have the C. This is out of the spectrum going out on the line. You have it's transparent for bit rates, modulation formats, not for the spacing because it's still a 50 gigahertz filter. You can control the power and you can control the spectrum, and you also have admission control. In the drop side, you have the D point here. This is where you can monitor the spectrum, and you can. It's a bit rate, it's transparent, it's modulation format. You can also see it regardless of the modulation format, and you cannot do anything else here because it's more or less just monitoring point. Dropping from the system, it's bit rate transparent again, modulation format transparent. It's not spacing either because it's a 50 gigahertz active filter, and you can modulate the power. So all in all, we have a quite good setup in this case by controlling everything and being transparent. Only thing here is the admission control at point A, where you can add an alien wavelength with a wavelength that we did not foresee. If we already are using that wavelength on the other port here, of course, we will have an interference in here. You can jeopardize existing wavelength in these 3 ports on this port here. So all these points here, A, B, C, and D, and E, they are monitoring points in our system, and that means that you can get alarms from these points. So this is very important when we are talking OAMP. So we can actually monitor this point, we get alarm back. That means that it almost looks like a native wavelength in the Alcatel system. Only thing that we cannot do is that we cannot map an object here in the network management system. We can do everything down here. This is done in the element manager, but this part here is normally an object, an Alcatel object that goes into the network management. That cannot be done. So we are actually quite close to having a normal wavelength going through the system from an OAMP perspective. So I'm just wrapping this up, and we have the spectrum. We have that. We have OK security for this one. We have here. We have the control of the power management. Still, this OK should go to the element manager. Network manager, no, we can't do that. Native systems in alarms in the native system in the Shannon, yes, they get the alarms. Alien system, that is the Alcatel, we get the alarms as well. So the remaining challenge here to interwork this, seen from my perspective with the 2 current vendors, is that we should enable communication between the 2 different management systems. And then, of course, we should take out the guesswork of the design and the provisioning in the P in the provisioning by having a modeling tool that can do everything for us. So, last but not least, we have the cost considerations. In this slide here, I show what it takes to do 200 gigabits between Amsterdam and Copenhagen. The slides are normalized. This is 100%, 10%, 1%. So this is also a logarithmic scale. First, we have some assumptions here. This is mostly about the labor and the work. This is maybe I should just explain what it is. This is the capex, raw capex cost. This is the power per year. This is the OPEX associated with labor, and this is the OPEX associated with configuration of the node. And we have made some assumption about how long time it takes to install an XFP, how long time does it take to install the different muxes, the line card, and how to configure the wave. And we have some travel times associated with the alien wavelength and the regenerated wavelengths. What's important to see here first, before we go into detail, is that the cost of the capex is magnitudes above the other costs. So no matter how we deploy this, it's always the capex for the equipment that is the most significant part. If you accept that you have an alien wavelength, as we saw in the previous slide, that you have a system where you can monitor the alarm and you can provision it. So those 2 things out of the question. Looking at this is still the cards, it's still the shelves that cost the money in the end. And that's when we are neglecting the guard bands. If you have wavelength extortion, then of course the guard bands are expensive to you. These are neglected, and the design rules are neglected. And this is, as I said, is that you have the alarm and management. It's possible. So it's difficult to see here what's. You can probably see there's a difference between those, the alien wavelengths and the regent. But let's see in another linear axis here. For 10 gig, it's roughly twice as much, and the same for these two. So we have made the assumption that a 10 gig card is 10 times as much as a 10 gig card, and a 40 gig card is 4 times as expensive as a 10 gig card. So this is confirms let's say the general notion that you are saving a pair of transponders, of course assuming that you can reach from point A to point B. So, just in time for my conclusion. Yeah, we have the VPI simulation platform for the alien wavelength, and it conforms qualitatively with the experimental results, which was very important for us. And this was one of our main goals with keeping on with this setup, trying to take out the guesswork of the provisioning. It's not perfect, and you can see we did not have the same power levels, but we had the same waveforms, and we are quite sure that we got it right this time, so we can change a little bit and try to optimize the VPI simulation. We also show that the 40 gig PMQ PSK together with the 10 gig signals, it's not a good combination. It's the same baud rate actually, and this gives the very big variations for power and guard band size. But it gives us, now we have worked with this design since 2009. Now we have the knowledge to put in other modulation formats. We have a good idea that it probably works better with 100 gig. You saw the presentation from Case Delart. They were using another modulation scheme and going from Geneva to Copenhagen. So we didn't have any concerns about setting that wave up because we knew exactly what to do, what to look for. We didn't make a simulation, but we had sufficient information. So it really was paid off well for this experiment. And then we saw for this combination of products and vendors that the OAMP is adequate for this setup. Not many steps is needed, at least not in the Alcatel system, to make the alarms go into our generic alarm system. It will not be integrated in the network management, but it will be shown to the NOC, and with the right procedure we can troubleshoot it just as we're troubleshooting everything else. And this is one of my main concerns, is that if you are deploying alien wavelength, you should do it as a service, not as a hero experiment, because we did that already in 2009. Hopefully we are evolving a little bit. And then for this mix of products, we are in the favor is for the alien wavelength approach. We are saving, just as you would guess, the additional region transponders, and as we showed, the transponders are still the main cost issue for putting up services. Lastly, but not least, we have the acknowledgement. Big thanks to SurfNet for providing the additional cards for the 40 gig, additional shelf installation in Copenhagen, Talinda's people doing all the calibration in the start of the network. Also to Nordernet for providing bandwidth on the link and the transponders. And last but not least, the research leading to this has been done under the SHANT project, SHANT 3. Thank you very much.
Okay, thank you, Rolf.
Thank you.
So this is open for discussion. So somebody have some questions? Lars? Okay, so.
Lars, very nice presentation. Very nice presentation. I mentioned that you have done experiments on true-wave fiber, and I expect that simulations have been done also on true-wave fiber.
Yes, that's going.
Did you perform any simulations for standard single-mode fiber?
No, we did the simulation mainly to verify the current setup, and then as I try to say that we will probably evaluate and change also the VPI setup. Okay. And that would be interesting to do it with the standard fiber. It would also be interesting to change the spacing in the VPI setup, but the simulation just took so long that we were not able to change that as many parameters as we would like.
Okay, thank you.
Klaus Grobe from Adva Optical Networking. I'd like to comment on the 100 gig in comparison to 40 gig with regard to the modulation scheme. I wouldn't be too optimistic because the 100 gigabit, not the 400 or whatever that comes there, but the 100 gigabit long-haul transport will in almost every case be based on PMQPSK, because that is exactly what the whole industry urged us, the vendors, to do to avoid the disaster with 40 gig. Because 40 gig never took off because, I don't know, 2 dozens or so of different modulation schemes were implemented, all of them were too expensive, blah, 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 blah. So what the industry today is doing with regard to 100 gig is exactly what OIF wanted us to do. So every long-haul system at 100 gig will run PMQPSK, and it will be a bit less susceptible to phase noise because it runs at higher baud rate, but that's it then.
Yes, of course, that was also what I meant, that we might see a slight improvement, but of course you're running with you can say the same configuration with PMQPSK. But it would be interesting to see how far you can go, because a lot of the communication with the vendors you're talking about very long reaches, but when you're mixing them or cascading them with different systems with and without chromatic dispersion compensation, there's a lot that can change. So we would like to go further with that and see if we can do this, maybe not in a large scale, but for specifically designed links. Yeah, thank you.
Okay, gentlemen, thank you again, Lars.
Thank you.
And now we will have a third talk. Vladimír Spotlacha from the CESNET. Time and frequency transfer as in all optical network as a new type of application.
So, thank you for the introduction. Good afternoon. So, my goal is to say several words about our specialized application, time transfer in all optical network. Just when we are speaking about time transfer, we deal with accuracy in order of nanoseconds or better. So it is at least 4 order of magnitudes better accuracy than in standard time services like NTP and other. So you may ask for what reason is such high accuracy necessary, and the answer is simple. It's just for metrology, especially for comparison of time standards. As a brief introduction, time standards significantly change in past century. Just from the precise mechanical pendulum that was used until the 30s years, then it was replaced by ONZ quartz oscillators, and in 50s atomic clocks were developed. It resulted in a change of the second definition, since the time second is not defined by the solar system, but only using the atom. Currently are in development new generation of clocks. It's so-called quantum logical clock. There is a significant difference between these clocks and the standard atomic clocks, as the output is not in microwave bandwidth, but this time in optical bandwidth. So it is possible to synchronize the frequency in much shorter time interval. So measurement is possible to do in a few seconds and not in several days. speaking about the time standards, the main task is to distribute the time. Definitely the most simple way how to distribute time is to use the electromagnetic field. We should take into account that 1 nanosecond is a really short time. It represents just 1 feet or 30 centimeters of light path in vacuum. So dealing with this time or shorter time is problematic once we like to transfer the time to distances over many hundreds or thousands kilometers. But for shorter distances, let's say hundreds of meters or few kilometers, there is no problem to use electrical cable or optical link, as the thermal dilatation of the medium is negligible. And as I said, what is important is the, let's say, 130 centimeters when we need to reach the accuracy about 1 nanosecond. Another well-known time distribution system is the DCF77. All of you probably use some kind of radio-controlled clock. That's just is application of this radio broadcast system. It is time distribution, but when we speak about time transfer, it is slightly different application. Time transfer means to compare two clocks in different sites, usually geographically distant places. Therefore, there must be used more sophisticated methods for time transfer. Currently are in utilization mainly 3 types of such methods. It is indirect transfer using that uses the navigation system, usually GPS. One of that method, for instance, relies on receiving signal of the same satellite. It means it can be used only in case the distance is not close enough that the same satellite can be visible from both sides. But it means it's usually 1,000 or 1 or 2,000 kilometers on the Earth's surface. Slightly more accurate system is two-way satellite transfer, but it is much more expensive. In this case, there must be rented two-way channel using some commercial satellite, and it is used for the best comparison of time clocks. And the last one is what is subject of our presentation or our test. It's the optical file, link time transfer. So, what was our goal? We just like to design some alternative method that can be comparable with common view GPS time transfer as far as concerns the accuracy and the distance. And we would like to use standard DWDM all optical network. Just to shortly summarize features of this method, it is a two-way time transfer. The optical signal is modulated by 1 PPS signal. 1 PPS, it's a term used in metrology. Output of precise clock is represented by electrical signal when the beginning of each second is represented by rising edge of electrical pulse. And for compatibility and in order to avoid any problems, just we decided to use standard SFP transceivers. This graph shows the simplified schema of our adapter. There is the SFP transceiver. SFP transceiver, as you know, is a very simple device. There is nearly no internal logic. It is just only a transformer between electrical signal, transformer that changes the electrical signal to optical signal and back. And the main part of the adapter is the FPGA chip, where are implemented few logical blocks. Most important of them is the modulator, which has two inputs. One is the 1 PPS signal from local clock. It means the signal that is subject of transmission. And there is also some local oscillator, which can be also synchronized by the atomic clock as well. And these two outputs are together modulated, and the result is the optical signal. We use our own modulation. It is non-standard modulation, but it can be compared to standard return to zero. So the ratio between the light and dark is about 50%. And on the opposite side is the same type of adapter. So the incoming signal is converted to electrical signal, demodulated, and the output of the modulator is the 1 PPS signal that represents the signal from the opposite side clock. And here is the time interval counter that simply measures the phase difference between local 1 PPS signal and 1 PPS signal from the opposite side. The second time interval counter is just an auxiliary device that allows us to reduce the noise, so it is not in principle necessary for the function of the adapter. The source of the noise is here in modulator, because there may be phase differences between these two signals, so we can measure them. So this photo shows how the adapter, the prototype of adapter, the first prototype, looks like. You can see there two desks. The bottom desk is commercial development board with FPGA Vertex 5, and the upper desk is our desk with interfaces. You see that SFP cages, and there are also some converters with standard outputs. Maybe you can ask why we don't use these two cages on that desk. There are also SFP cages, but that SFP is connected through Rocket I/O on the desk. But we need to avoid this Rocket I/O. We just directly control the SFP pins by the FPGA chip. In last 12 months we made several experiments. Most important of them are three that I will briefly describe here. It includes the measurement on optical loop, where we just try to verify our method. The second one was real-time transfer between Prague and Vienna. That was mainly for demonstration purpose, that this method is really usable for the time transfer. And the last one was exact measurement and comparison with commercial common view GPS time transfer system. Definitely there are many participants. on these experiments, it includes Czech and Austrian time and frequency laboratories, the Austrian NREN Aconet, and University of West Bohemia. So here is the skeleton of CESNECT DWDM production network. Important is this production network. It's real traffic on this network. So main node in Prague, the second main node in Brno. Here is Vienna, so we have cross-border link from Brno to Vienna, and the Pilsen city is just here. As I said, the experiment was done on the circle, so it is just this one circle. There are together 12 amplifiers, and if you see some zoomed of this picture, there is also described the length of each segment. So in that optical experiment, both ends of that link were terminated on the same table in laboratory. The total length of this loop is 744 km plus unknown length of compensation fiber. It is just the real fiber that is provided by fiber owners. As I said, there are 12 amplifiers, and what is also important, one segment of this loop is realized by optical fiber installed on top of electricity distribution poles. So such optical cable is subject of very rapid changes of temperature and therefore length dilatation compared to fiber that is in airs. Here is another map of our network. So circle link to Vienna and Prague and Pilsen. As concerns results of the first test, the optical loop, we measured one-way delay on this loop in both directions. Here is the result of the measurement. It lasted for 6 days. You see significant changes of delay every day. It is just, and definitely it is some record of weather, just that this day was cloudy. And while in other days were nice sunny weather. Just the fluctuation in every days, in every sunny days, was about 130 nanosecond. But when we just subtract these two data, we have the residual asymmetry of the link, and here is the asymmetry smaller than 2 nanosecond. So it is a really good result. As I said, 2 nanosecond represents about 60 centimeters of length in a vacuum, so about 40 centimeters on fiber. This graph is typical description of results in meteorology. So let me allow to explain it. The y-axis shows the time deviation in logarithmic scale, and the x is the time interval over which that time deviation is measured. The beauty of this graph is that the slope of some linear part exactly shows the type of noise that is dominant for this interval. So this slope, which is minus 0.5, minus 1/2, means that it is normal white noise that which origin is in the adapter. And this point is just the best result of the measurement, and says us that for the averaging interval, for measuring interval of about 500 seconds, we reach the accuracy or the time deviation about 8 picosecond. Just then the graph goes up, and here is the interval that represents about 1 day. So here are that daily fluctuations of temperature and therefore of length of the fiber. The second experiment, time transfer between Prague and Vienna. In this case, we use 2 rubidium clock, one in Cessnet. This clock is controlled by GPS. Unfortunately, in Vienna, wasn't possible to reach the BEV, the time laboratory, by optical fiber. So just people from that laboratory moved their rubidium clock, running rubidium clock, to university, where is terminated the link from Brno. And therefore this clock was free running. The length of a link between Prague and Vienna was slightly more than 500 kilometers, and just again, it was part of this link. The Prague-Brno and Brno-Vienna represent production network. So here is the result. In this case, has no sense just to show some graphs in the previous case about the noise and so on, because the clock is free running, and just what we see here is that some linear change of offset, and it is simple from that graph to calculate that the frequency offset of the clock is about 8 times 10 to minus 12. It's standard inaccuracy of rubidium clock when it's free running. Here is also visible some interesting incident. Just people from, or my colleague from Brno, forgot about the measurement and replaced optical amplifier. And we simply measured from this data, or we can interpret this data, that in one direction they add, or that the new amplifier has compensation fiber longer for 14 meters and in the opposite direction for 3 meters. It is important just to put stress on this incident, because it shows how this method can be easily destroyed by some unexpected changes of the link. So it must be carefully take into account that the link is just utilized for similar type of measurement, and every changes of patch cords or amplifiers must be done in under some control. Definitely, once we provide the measurement during the change, we can simply measure it and compensate it for the future time. So, but if such change will be done between two measurements, we will receive the next time bad results. And the last one experiment, it was the comparison with GPS time transfer. In this case, we use just again rubidium clock that we moved to Plzeň, to University of West Bohemia, and this time the second site was in the Czech Time and Frequency Laboratory in IPE, and there was used the cesium clock, which represents our official time scale, the Tempus Pragensis, UTC-TP. The length of fiber in this case was 150 kilometers, and the geographical distance slightly less than 100 kilometers. In both sites we install the commercial GTR50 device that measures the time transfer using GPS signal. So here are just the same data of the measurement. It is it represents observation of one of the same GPS. So every GPS satellite is above the horizon for about 4 hours. This measurement is slightly shorter than 4 hours, and more important, definitely, the second graph where is eliminated the frequency drift of the free-running rubidium clock. Green data represent the measurement from GTR50. That blue line is some averaging of this data. The average is calculated for about 15 minutes, and the red represents the result of optical transfer. So without any other processing, we see that there is very good correspondence of all this data. Just this interval is 1 nanosecond. But definitely the same type of graph for time deviation, that green data from GPS measurement is this dotted line, and optical measurement is just this line with squares. For comparison is added direct measurement when we later move the rubidium clock to IPE. We install it in the same room as at cesium, and we compare them. So this just to show how what kind of reserve we still have in our adapters. So definitely we should to improve the noise somehow. And here is another representation of the measurement. It is just direct comparison between optical measurement and GPS. We can see also just again some influence of daily changes of temperature or some other effects with 1 day period. But we should conclude that as the GTR50 has the accuracy about 1 nanosecond, so it is, we can say that the accuracy of the optical measurement was not worse than 2 nanoseconds, probably slightly better. It is difficult to distinguish what of these inaccuracies are caused by the GTR50 and what of by the optical transfer. Yeah, thank you. So, some conclusions. Definitely we tested our and verified our adapters and our method. What is extremely important, there was observed no interference between this application and the production traffic. And we demonstrated or shown that commercial network, commercial production network is possible to use for such kind of application. we proved that very good agreement with common view GPS method, and we receive very good time deviation, less than 10 picosecond. So it is something we didn't expect originally. And as far as concerns future work, in few weeks we will build optical paths between BEV in Vienna and IPE in Prague. It means between two national laboratories. As some times ago, finally, colleagues in Vienna succeeded to rent about 3 kilometers of cable between university and BEV. We are going to start some long-term measurement and to convert this experimental method to service. And definitely, in order to extend our measurement to other sites, we are currently limited by cross-border DWDM links. So we currently try to just to use this method or similar method in the scope of future GN3 backbone. So it's our primary task for following year. Okay, thank you.
Okay, thank you, Vladimir. And some question to this? Okay, so go ahead.
Hi. First of all, I would like to ask, what kind of SFPs are you using? And is the signal from those SFPs, is that carried as an alien wave over the network, or is that regenerated in the DWDM equipment?
It was regenerated. It was or not? Just maybe. Sorry. Okay, it wasn't regenerated. Yeah, sorry. There is no regenerator in the meaning conversion to electrical signal and back. It is not possible. It is non-standard modulation. So it is pure all-optical network.
Okay, so then what kind of SFP were you using?
It was standard, the DWDM SFP.
Oh, it was DWDM SFP?
Yeah, definitely, yeah.
Okay, so frequency stabilized?
Yeah.
Okay. Thank you.
Somebody else? Okay, thank you very much once again. And I would like to invite you for another events which will start at 6 o'clock. So there are many extra events, which is, for example, the ADVA Optical Networking Workshop. If you are interested in the optical, of course, there are some perspective on web conferencing, the Huawei telepresence, and so on. So thank you very much for visiting us, and so hope I will see you again sometime.
You want to run the reading, I think, from here to the bottom over there.
And the precondition on the large system, right?
Yeah. So we just need internet on the sensor. I need to install just a small area. So we'll need the protection from this one as well. So once again, the video will be divided into hardware. So that one will be displayed on this projector here. And then you have the audio going to your mixer. So you won't be sorry, come again? You won't be using the television order. Oh, the television? No.
No, you use the screen
Yeah.
for the picture from the...
Yeah, from